our first speaker is going to be Mr. Nicolas del Rio. He's going to talk about declarative visualization generation. He's working with Dr. Paso, right? Okay, so let's welcome our speaker. We have 15 minutes for presentation, 5 for questions. I'll remind you when we're running out of time.
Thank you. Okay, so declarative visualization generation. This is our approach to generating visualizations as opposed to generating visualizations writing pipeline code, which I'll show. So the objectives of today, I'd like you guys to walk away here knowing a little bit about what a visualization query is and the purpose of it, where it fits into this visualization scenario. I'd like to also help, hopefully you guys will understand a little bit about the infrastructure that supports the answering of these declarative requests that we call visualization queries. So the premise of this work here is that we think that users naturally think of visualization generation in terms of declarative requests, meaning we think users know what they want, but they may not necessarily know how to generate what they want, by either writing a program or a pipeline, as you'll see. For example, a seismologist who has velocity data might be thinking, well, I want to visualize my seismic velocity modeled data as a set of 35 isosurfaces. So here you see this is purely declarative. They're specifying what they want. They want their seismic velocity projected as isosurfaces, 35 of them exactly, a property of that. Nowhere does it say anything about how I'm going to generate that. And just to show you, they would, this is the visualization that actually satisfies that request. I'm not going to go into too much detail on what this means because it's not the focus of this presentation, but I can tell you that this visualization right here satisfies that request. These are isosurfaces, so every point along these planes are the same value, and every plane is drawn at equal intervals. So the areas where the planes are in close proximity, that indicates a rapid change in the data. The problem is, though, however, toolkits such as Visualization Toolkit, and I'll describe what a toolkit is right now, they don't process requests. Visualization toolkits are software suites, and they contain visualization modules called operators. And it's up to the users to program against these operators to build visualization applications. More specifically, they don't just build any application, they build what are known as visualization pipelines. And a visualization pipeline is very simply, here's the code for a pipeline, but we'll abstract that out a little. Pipeline is simply just a set of visualization operators that are chained together. So the data flows between the operators, and each operator does kind of some transformation process. So if you see, the first operator would consume the input data. By the time it was processed by the operator 7, it would generate those isosurfaces. At any point within this pipeline, the data is in some intermediate form between its raw form and its visualized form. So that's what users have to do. So let's take a look at this just a little bit more in depth. This is actually Java code that generates that visualization that you saw in the slide 1. I grouped it in such a way to show you the operators. So each little segment corresponds to the instantiation and configuration of some visualization operator. The data flows between them, as you see from this kind of abstracted view. This is a challenge because each one of these operators serves a specific function, a specific purpose, and the users really need to understand what these functions are in order to chain them properly. So the first operator is actually called the data reader, and these actually terms, you may not, when you work against one of these APIs, the VTK API, they're not going to name them this. I've actually named them what the literature has named them. For over 20 years of visualization literature have identified these components. So the first one is a data reader. It's responsible for consuming your raw data set and transforming it into a form that the other operators, the VTK operators, can operate on. So the next one is a view mapper. It actually takes that the data that's read in and actually extracts those polygons that you saw for the isosurfaces. And then there's more transformations, finally a rendering, takes that geometry, turns it into pixel data. Finally, it dumps it as a JPEG. So like I said, users, we expect users to do this. The scientists who may not have any computer science background to say if they want to visualize their data, well, here's a toolkit, program this. It's quite challenging. Additionally, each one of these operators are heavily parameterized. And the parameters, of course, control, fine-tune the behavior of what the operator is doing. They're so important that you could have the right operator, the right sequence, you could have the right pipeline, the correct sequence of operators, but if you don't correctly specify these parameters, you can yield a visualization that's very misleading. Perhaps the resolution is bad, perhaps it's hiding some features in the data. So these parameters are just as important as the sequence of these operators. So the challenges with this, I've kind of already alluded to some of these challenges, is visualization toolkit users, although we think that they're thinking in this declarative mind frame, ultimately they have to transfer or transform this declarative specification into these pipelines. So it's the difference between declarative versus imperative code. So users need to understand what pipeline operators are going to be included, what operators they should put inside their pipelines. How to transform your data sets into forms that can be ingested by the pipeline operators. Many times you'll say, aha, I found this function that generates the view that I want, isosurfaces or volume, but it only consumes data in format X. My data is in format Y. How do I transform it into that format X that the operator can consume? Additionally, how do you correctly set these parameters? So we believe that users think in terms of these requests, and therefore writing these procedural pipeline codes may not be very intuitive. And not to mention, it's also kind of challenging. They need to know a little bit about programming and visualization toolkits in general. There are many toolkits, and even deciding which toolkit to pick can be a pain. So can we do better? Well, if we look to the database community, we've seen that database users have long relied on issuing declarative requests. They issue them in SQL, structured query language, to manage their data. They don't write code to do the joins and selects and all these complex relational algebra operations. They just specify a query, and voila, the system knows how to transform those queries into what are known as query plans. And if we think about what a query plan is at the conceptual level, a query plan is just a pipeline. Instead of visualization operators, though, they're relational algebra operators, and they actually compute the results specified by the query. So why not apply kind of the same query answering paradigm to a visualization setting, in which users request for visualizations using some kind of SQL-like notation, which we call visualization queries. And then let a reasoning, defer the generation of the pipeline to some reasoning system that, given a query, knows how to derive the pipeline that will generate a visualization that satisfies the query. So that's kind of our work with our declarative visualization request. So specifically, visualization query, as I said, it's a visualization request in some machine-readable form. And I'll show you an example of what one looks like. So if we wanted to generate those velocity isosurfaces, we would write this query. You can see that I've broken the query into the 3 sections to kind of highlight the components of these queries. The first section specifies the view and viewer. So this is saying, select isosurface. I want to see isosurfaces, and I want to be able to see the results of these isosurfaces in my Mozilla Firefox, for example. There's other viewers too, but this is just a simple one. The second kind of clause of the query is the data characteristics. So you do need to write one of these queries, you do need to know a little bit about your source data that you want to visualize. So you need to know where it's located, a URL from this URL. You need to know the format, and you need to know the type. And finally, the bottom section is reserved for the parameter bindings. So this is where we say, well, these isosurfaces, I want it rotated 104 degrees about the x-axis, and I want 35 of those contours. So that's a visualization query, and we're trying to see if we can move people to start using visualization queries instead of writing these pipeline code. But just because we have a query language, I'm going to talk a little bit about the system that actually can satisfy these queries. So just to highlight again, here's the old way, here's the new way. It's much more concise, and we think it's easier, but we're going to conduct a user study to see if it's really easier for users to write this rather than the pipeline code. So the challenges with the query is what kind of supplemental knowledge is needed to derive the pipelines from visualization queries. What does the system need to know to be able to take a query in and automatically generate that pipeline? Because we're talking about knowledge, we're capturing facts in some kind of formal manner. And because we're capturing facts, we need to decide what's important to capture about these operators. And because we're only selecting a subset of all the properties that these things have, we're talking about a model. So how should we best model the visualization processes? Finally, once we've come up with the model, which we have, and fortunate literature for the past 20 years have come up with very many different various models for different purposes, maybe for user understanding. Nobody's ever come up with a model for automatic derivation of these pipelines. So we kind of looked at the literature and we picked kind of the best parts from the different models, and we came up with our own. But once we came up with our own, we needed to make sure that most of the toolkits would conform with the model, or there was some way to view all the operators from the toolkit and map them to our model, and that's been the case so far. So I'll talk a little bit more about this knowledge that you need to represent, the system would need to know to derive these pipelines. So visualization knowledge is just that. It is the knowledge needed to construct a visualization pipeline. Everything that the user needs to know, we've captured to build a pipeline, we've captured this in a machine-readable form, and we've fed it to our inference engine. It focuses on a toolkit operator capability and classification. So what formats does the operators work with? What is their function? What is the role within the pipeline? The format transformation rules. So there's rules saying that every pipeline must have a view mapper, because a view mapper is the thing that generates a view. In order to link two operators in succession, the output format from one operator needs to match the same input format. So simple rules like that, we've captured those in logical rules. Additionally, we've actually captured the invocation protocol. So does it need to invoke Java code? Is it a web service? We captured all that using semantic web standards. So we actually use the web ontology language OWL to encode our visualization model and all the operator knowledge of the different toolkits. We've used Swirl semantic web rule language to capture the rules, and OWLS services to describe how to invoke these services. So what we've done is all the toolkit operators, we publish them as web services, and OWLS tells us how to invoke them. So given this and a pellet reasoner, so once you have all this knowledge, you need to be able to infer the relationships between the pipelines or the operators to build these pipelines. So we've adhered strictly to semantic web standards for this solution. So I'm going to describe a little bit, at a very high level, on how you would automatically compose a pipeline, just to show you that it is feasible, it is possible, and it's not as complex as it might seem. So the query, given a visualization query, the query tells you a little bit about the data. It tells you that it has some format, in this case, binary float array. And you want to project it to some view, isosurfaces view. So this is the query for those velocity isosurfaces. But we also have the additional information. We have the visualization knowledge. Visualization knowledge will tell us things about the operators. So we have this thing called VTK operator. It has an input format VTK image data and an output VTK poly data. And this particular operator generates isosurfaces views. So we have a match. We see that both the query and this VTK operator reference isosurface. So we know for sure that the pipeline that will answer this query needs to contain that operator in there. So the problem then becomes, well, this thing ingests VTK image data, but I got binary float arrays, so how do I transform it to the VTK image data? And using the other knowledge about the transformation operators and the pipeline rules, we can infer that actual pipeline, and that becomes one segment of our visualization pipeline. And this is what the system is doing automatically for us. So I'm going to show you a little example of what it looks like to submit an actual query. Here's our query box. So suppose we had a request that said, I'd like to visualize a gravity data set. It's encoded as a table of ASCII characters. It's a raster map that I can use in Mozilla Firefox. And my gravity data happens to be located here. We could translate this request very easily into a visualization query because they're both declarative. Here we see select a raster in viewer Mozilla Firefox from this URL from this data with the format type delimited data set and the type D19, which means gravity data, but I'm not going to discuss how you map between those, but this is what the query would look like. You'd submit it to our engine, and you would see a result. Now this is interesting. You might be expecting one result, but because we have knowledge about not one toolkit, many different toolkits, we provide the environment that you can get many different visualizations. In this case, the system knew how to generate 12 different pipelines, all that generated different visualization that satisfied the properties specified by that query. It's kind of neat. So if you were to click on the visualization image, you're provided with one possible visualization. Also though, say like, well, I'd like to know the pipeline that was inferred that builds that visualization. You can also click on that and you're provided with, this is actually the pipeline description that's presented to you, that VSCO presents to you. So this is very much just like the pipeline code. Just know that this was automatically derived. So each one of these is some operator, and data flows from the operators just like traditional pipelines. It's a very simple pipeline, only 3 operators. You see that it tells you a lot of different things, like the type of the operator. This one's a transformer. This is a mapper, so this one actually generates a view. This operator actually generates that raster map. This is another transformer. Just transforms it, the output of this raster map, which is PostScript, into ping, because you said you wanted to view it in Mozilla Firefox. Mozilla Firefox can't by itself render PostScript, so we had to transform it to a ping image. Now Mozilla Firefox can provide it to the user. There's a lot of, it tells you the parameters, all the values. So in this case, it used a lot of default values for the parameters, for the colors, the fonts. In addition, these are links. And if you clicked on any of these links, you'd be provided with the RDF, which is the knowledge. You'd be provided with the knowledge description of this operator. So in this one, what's interesting about this particular pipeline is this first operator actually was supported by generic mapping tools, a toolkit. The second one by NCAR command language, NCL operator. And finally, GoScript did this final transformation. So we have a hybrid pipeline. So not only do we have multiple different visualizations, because we're describing the functions provided by these toolkits using this one model, when the system needs to build a pipeline, it doesn't really care what toolkit it came from. As long as the operator satisfies a particular function that it needs, it's going to use it into the pipeline. So here we have a mixture of toolkits, which is something that is not too common, but it provides greater flexibility and more possible visualizations. So what do we apply this to? Well, we've used this at this old Grand Mountain, I think it's gone now, but Paces here at UTEP. And they worked a lot with environmental data, or gravity data, and we actually use Visco to transform the gravity data to various different representations. So we have different visualization queries to generate those maps. Additionally, I participated in an internship at NASA over the summer, and they have an online platform called Giovanni for doing data analysis, and the primary tool for analyzing data is through visualization. So they were very much interested in Visco because although they generate visualizations, they're using the old way. They're manually hard coding the pipelines, and when a toolkit changes or they need a new one, they have to change the pipelines. So they're very excited to use this approach, Visco. So all they do is register new operators, and Visco will consider them, or our visualization query system will consider using them. But the query, the request for those visualizations stays the same. They're very interested in that flexibility. So although they have thousands of different kind of data, I did a prototype proof example to show that I could use Visco visualization queries to render this brightness, temperature, and aerosol data as various time series plots. Finally, here at CyberShare at UTEP, I've been working with the active seismic data that is processed by the whole inverse tomography algorithm. And here's some of the visualizations that were output of those. Once again, all these visualizations generated from different kinds of data using visualization queries. Okay, so conclusion, visualization queries provide an automated alternative to manually constructing toolkit-based visualization pipelines. We want people to use queries. We don't want them to do the old way of writing code. Pipelines can be automatically derived from these visualization queries, provided you have the right visualization knowledge. So if you don't have the knowledge about the toolkits, you could write a query and it might say, I can't answer it. I don't know of the right operators that can satisfy your request. Visualization queries have been used in projects from earth science, environmental science, from NASA to organizations here at UTEP. And currently, we're actually conducting a user study, and this will kind of finalize my dissertation. To really see to evaluate if writing and reading these queries is easier than writing and reading traditional procedural code. And what we're going to do is we're actually going to find participants who are already experts, or they're familiar with writing BTK pipelines or GMT pipelines, and see if they can get a better performance writing and reading pipeline code than their visualization queries rather than the pipeline code. And just a few acknowledgments. As you said, my advisor, Dr. Palomino da Silva, Timothy Lebo from the Air Force Research Lab, and RPI. He's been providing me from his perspective of what he would need a system to do. We've been trying to accommodate him and making sure the queries satisfy his needs. Gregory and Chris Lintz from NASA, they gave us kind of the NASA perspective. They said, well, if you did have this language, we needed to do this, so we needed to make sure we satisfied them. Finally, Dr. Romero and Dr. Yana Pennington here at CyberShare have been kind of a little bit co-advising and providing good feedback on my work. So that concludes this presentation.
We have a couple of minutes for questions.
So, getting from this pipeline programming language to abstract queries, you had to make some assumptions about what the code should do and what, right?
Yes.
To make it abstract enough to be such a simple language,
yes.
Right? How did you choose those assumptions, and how configurable is it?
Well, configurability, obviously, because it is simplified, you can't do everything. You can't answer all. You can't generate so if you're writing procedural code, you could make these pipelines very complex. You could have multiple pipelines feeding into each other. But we chose a very simple model. Like you said, we had to make some assumptions. So our pipelines are just these straight linear things. And if the queries can only be derived into those simple pipelines. But as far as deciding what to leave out and what to capture in the knowledge, we diverted to the literature. And there's been lots of work on modeling visualization pipelines, and we kind of reviewed a few of them and took like a decent balance that we needed. So we're hoping another evaluation would be how expressive is a language? Can it satisfy your visualization needs? And I would tell you that there are some limitations to it, but for the most part,
It does what you want.
It's done what we wanted to do for NASA and for these other places, but I can think of specific scenarios that it wouldn't work in. So.
Okay, well, time for one more question. Okay, so I have two quick ones. What's the size of your knowledge base, number one? And number two, you must get a combinatorial explosion. So how do you choose? You presented 12.
Okay, the first one, the size I'll measure is in statements. So we have a knowledge base, and there's statements being made like operator X does this, operator X, and in terms of statements, it's about 6,000 statements, just to support those scenarios that you saw. Combinatorial explosion is a problem. It's even a bigger problem because in the query, you can use the wildcard. So you can say, I want isosurfaces, but if you don't know what view you wanted, you can put an asterisk, and it'll generate every visual, and you'll have that combinatorial explosion. We don't have a solution for that. Maybe preferences. Maybe a user says, well, I only want pipelines from GMT and NCL because I don't like VTK, or it doesn't give me the performance I want. But we haven't solved that problem yet. So.
All right, let's thank the speaker again.